that was all fine and dandy because we had examples of relevant and non-relevant documents. So what happens when you don't? What happens when you just have a query? And the answer is you cannot estimate PW and QW, at least not directly, at least not in this model, not unless you come out with a more powerful model. And we're going to look at one in the next lecture. But in the context of this model, you can make some further assumptions, and these will look increasingly silly, but they will allow us to massage the formula into a form that can, where we can estimate something, right? So that's what we're massaging. We want PW and QW, but we don't have any examples from which to count PW and QW. So what are we going to do? First, we're going to make a strange assumption. Now we're going to look at the query, and we're going to say if the word W was not in the query, then we're going to assume that PW and QW are the same. Okay. So what does that mean? It means that if the word was not in the query, it's equally likely to appear in the relevant population and in the non-relevant population. Is that a reasonable assumption? No. Right? That blatantly tramples over all kinds of co-occurrence that you have in text, and is just plain wrong. You should have a bad feeling about that assumption. So it's a bad assumption, but it does allow us to do something useful. Right? It allows us to restrict the product further, because think about it. So this product goes over all the words in the document. Some of them will occur in the query, some of those words will be in the queue, some of them will not be in the queue. For the words that are not in the queue, PW is the same as QW, so that's going to cancel, and that's going to cancel as well. So all the words that are not in the document are going to magically drop out of this formula. What I'm going to end up with is the same product, but now restricted to the intersection of the query and the document. And you look at that, and something should tingle in your head right away. Yeah, you should think back to our indexing lecture. Remember, term at a time, you can only use it for quasi-linear functions. Quasi-linear functions are basically where you're computing something like a dot product over the intersection of the document and the query. And that has that form, right? If you just take a log of that, it's going to look a bit more similar to what you want. So that is in terms of the intersection of the document and the query. So right there and then, you know that by making that ugly, horrible assumption, I've now allowed, I can now evaluate this model really, really quickly using term at a time execution. But we're not going to stop here because we still have the pesky PW, and we don't have any way of estimating yet without relevant examples. So the next assumption, it's going to look even more bizarre. I'm going to say if the word does occur in the query, then PW is going to be a half. Okay. So if you're trying to interpret it, what it means is any word that's in the query, on average, is going to occur in half of relevant documents. Again, blatantly false, not ever going to hold again. But what it allows you to do is it allows you to get rid of PW for good. Right? Now we can cancel PW and 1 minus PW. Right? So why can we cancel it? Well, because we basically made an assumption that allows us to cancel it. So we're taking an arbitrary step. We have no idea how to estimate PW. We want to get rid of it, and getting rid of it corresponds to making that assumption. Right? So you can do crazy things in probability just as long as you encode them as assumptions and make them sound roughly sort of semi-formal. Okay, so after you do that, you're just going to end up with that part. Right? So we have a product over the intersection of the document and the query, 1 minus QW over QW, and here we need to estimate QW, and again we don't have any examples to estimate QW from, and what we don't want to do is we don't want to make another stupid assumption and just cancel it altogether, because then we're going to end up with 1 and we're not going to be able to rank anything. Right? There is a limit to how far you want to go with those silly assumptions. So we're going to make an assumption that is not silly at all, and that assumption is to estimate QW, we need examples of non-relevant documents, and nobody's giving us those examples. But what we do have is we have the web, or if you're not on the web, then you have your collection of documents. And if you think about the task you're solving, you're trying to identify non-relevant documents. Well, for any given query, almost the entire collection is non-relevant. That's just a property of the queries that humans construct. For any query you concoct, only a tiny, tiny fraction of the documents is going to be relevant, maybe 0.001%, and the rest is going to be non-relevant. So if I take my entire collection of documents, it's going to be 99.99999% non-relevant, and then there's going to be a sprinkling of relevant things in it. So for the purposes of estimation, the entire collection is a really, really good example of a non-relevant set, because the amount of relevant stuff there will be completely swamped by the non-relevant documents. So what I can do is I can take my entire collection of documents and use that to estimate QW. And it turns out that that is a really, really good estimate just by definition of relevance, right? Relevance is restricted to a tiny, tiny subset. So if you ignore that, if you estimate it using the whole set, then you're going to be really, really close to the non-relevant set. So what you do is you take NW, that's how many documents overall contain the word W, and divided by the total number of documents in your collection. And once you do that, you take those numbers. You would naturally, you do the same thing. You would smooth the counts, right? So you would add 0.5 to NW. You add 1 to N just to avoid extreme cases. And then you simply plug this into this formula right there. So for QW, you're going to get NW plus 5 over N plus 1, and then 1 minus QW is just going to be N minus NW plus 1 minus 0.5, so just plus 0.5. So you're going to have N minus NW plus a half divided by NW plus a half. So overall, it's going to look like that. And if you imagine, again, taking a logarithm of that product, you're going to have a sum that goes over the intersection of the document and the query, and then you have a log of this ratio. And if you look at that, you should recognize IDF. When we talked about the vector space model, IDF is that weight that you assign to words that makes rare words more important and frequent words less important in the similarity function. And that is exactly the IDF weight. And this is no accident. That is how the IDF was derived. So it didn't come up from some vector space guy tinkering in his basement with logs until he came with something that worked. It actually came out of the probabilistic model. And it turned out to work really, really well. And the reason it works really, really well is because it is a very good estimate for the probability of the word in the non-relevant set. It's just... so that's your IDF. So the whole formula boils down to a sum of the IDF values for the query terms in the document.